We are on chapter 8, part 1. And in this chapter is just a continuation of what we did last time. It's emphasizing on Sn1. I think we finished chapter 7, if I'm not wrong. So we are on chapter 8, part 1. And my computer is acting up, but I'll try to start as soon as I can. Let me see. Did we do part 1 already? Can someone tell me? It looks like we went over this. So we did up to electrophile. So chapter 8, part 1, I think where we stopped is 8.31. And that's slide number 17. That's where I'm continuing, and it says electronic effects. So just to give you a refresher, remember this is Sn1. To give you a refresher, Sn1 goes through formation of carbocations. So there's going to be a carbocation formation. And if there's carbocation formation, expect shifts. Under shifts, we talked about this before. Expect methyl shift. Expect hydride shift. The group migrates with the bond. Okay. Again, Sn1 will prefer tertiary carbocation over secondary, over primary, and in fact CH3 plus will not, even primary will not want to do Sn1. Never consider sp2 and sp carbocations. I remember someone asked me that question. I forgot who did. In other words, you don't want a plus sign on a double bond. You do not want a plus sign on a triple bond. Those ones are highly unstable. Never consider those. And then the other point we talked about last time is that under solvent effect, you want protic solvents. Why do you want protic solvents? For two reasons. The protic solvent will use its lone pair to stabilize a carbocation. Okay, and the protic solvent, let's see. The protic solvent, you see here, you have stabilization. The protic solvent will also keep away the leaving group. So if the leaving group is like bromine, after it leaves, you get it bound to the hydrogen. So those are the two reasons you want protic solvents. You don't want protic solvents for Sn1. You want aprotic for Sn1. Remember, protic solvent is the solvent that has hydrogen bonded to oxygen, nitrogen, or fluorine. So for today's lecture, we're gonna look at this point on carbocations, and like these first three are the key. And then we'll do the mechanism of Sn1 reaction. So now let's flow in. Electronic effect. So before I continue, let's define what a carbocation is. Remember, like I said, you already have your what happened? You already have your recorded video, which I'll fix. So let's first of all define what carbocations are. Follow it up with the recorded video. So carbocations, these are just compounds having carbons with plus charge on them. So I'm gonna draw random carbocations here, and then I'll want a volunteer to tell me which is primary, which is secondary, which is tertiary, which is methyl carbocation. So I'm just drawing them randomly. So I'm gonna call A, B, C, D, E, F, G, H, I, J. Let's start with A. Is it primary, secondary, tertiary? Volunteer? A, what is it? Is it a primary carbocation, secondary, or tertiary? Can you guys hear me? Why are we so quiet? Let me see.
Is it tertiary?
You make me feel like I'm by myself here. The first one is tertiary, correct? Because I see the carbon bearing the plus charge is bonded to 3 other carbons. So this is tertiary. Second one, B. Please, let's save time. Give me the answers. What's B?
Secondary.
Agreed. C.
Primary.
Agreed. D.
Primary. Secondary. Tertiary.
Tertiary. You have the 3 carbons. Okay. E.
Methyl.
Agreed. That's a methyl carbocation. F.
Secondary. Secondary.
Agreed. Thank you very much. G.
Tertiary. Tertiary.
Agreed. Thank you. Again, I see 3 carbons bonded to C plus. H.
Secondary.
Secondary.
You can open the door for me.
Someone go open the door for the kid.
Sorry about that.
I.
Tertiary.
A little sweet kid. Don't worry. That's what I'm going. That's what's going on in my house right now. J.
Primary.
Primary. Only 1 other carbon. All right. So thank you for that contribution, and you're making me feel good because it means you're attending. You know, some students will just turn on the Google Meet and run away. So now let's talk about carbocation rearrangements. I'm really trying to make sure my handwriting is readable. So remember, for Sn1, it's going to prefer the tertiary over the secondary, over the primary, over the methyl X. Now, why? Let's take an example of this structure. So, you know, if you have the more the alkyl groups you have, and you hear this in the video, the more the alkyl groups you have, the more stable the carbocation. What do I mean? The carbocation is going to be comfortable. That's what stable means. And it's going to have a longer lifetime. So the hydrogens will kind of donate the electron density through bond. So you have so many electron donation through bonds towards the plus sign. So this plus sign right here is kind of neutralized. Okay? It's kind of neutralized. Kind of. I'm saying kind of because it's not going to completely be neutralized. So compare the tertiary to the secondary, okay, such as this one. You're losing one metal, so you only have the baby hydrogen. So you don't have much of the electron donation inside the structure. You don't have much of the electron donation inside the structure. That's why tertiary is more stable than primary. And of course, the worst in this list is the metal carbocation, because all you have is the babies, which are just singly contributing towards the carbocation. Here in tertiary, you see how many arrows you could draw. So many arrows contributing towards the C+. So that's why tertiary is more preferred than secondary. Secondary is more preferred than primary. Primary is more preferred than metal. All right. In the case of primary, you're going to have two hydrogens. And let's say, for example, a metal. It's not always a metal. It could be an ethyl, a ring. All we are saying is you have one alkyl group on primary. That's why it's primary. So that's the reason. Now let's talk about the rearrangement. The key term here is rearrangement. Otherwise, I'm going to use the term shift. Another alternate word that I'll use is migration. All these refer to the same thing. So for example, if you do a reaction, let's say you have this alkyl, this carbocation, for example, this alkyl bromide, and you are trying to do Sn1. Obviously, the first step is for the leaving group to go. So you're going to get your plus sign right there. What type of carbocation is that? Someone tell me.
Secondary.
Okay, it's a secondary. It's not as comfortable as it should be. So the molecule will inspect around the structure and ask itself, can I do a migration? Can I do a shift? And then it's going to look at the neighboring carbons. So the neighboring carbons are called beta carbons. It's going to move or shift a group from the more substituted beta carbon, which happens to be this one down here. So on here, there's a hydrogen that's not shown. And then you have the CH3s. So one will want to move the smallest, the babyest group on the more substituted beta carbon, which is this. So I'll move the hydrogen. So in this case, the shift is going to be H shift. So the shortcut here is to tell yourself you're just swapping the positions. So the plus sign goes where the hydrogen was, and then the hydrogen goes where the plus sign was. Remember, you have one hydrogen there. There are 3 bonds. That's why you have a plus sign. You're missing one bond. There are 3 bonds. So once this hydrogen moves, you're going to have 2 hydrogens over there. Okay? And now the plus sign is down here because you stole a bond from the more substituted beta carbon. Now this is a tertiary. So this is the rearrangement. This is the migration we'll be emphasizing on in this class. So only then will the nucleophile come in, because you know Sn1 we said is unimolecular. So only then will the water come in to attack, and it can do it from the top face or the bottom face. We'll talk about that later. And so you get what we call an oxonium ion. That's the chemistry term. Why am I feeling hungry all of a sudden? Oxonium ion. You make an oxonium ion. Now remember, you use one lone pair of the water, so we have to have a plus form of charge. Oxygen likes to have 2 bonds. Now you have 3 of them. So that's oxonium. Now that's not the most comfortable. So another piece of water molecule will come to remove this extra hydrogen. So you get the final product, which is an alcohol. And then the water that did the proton transfer, which is usually the last step whenever you use a protic nucleophile to attack. that water is going to be turned to H2O plus because it gained an extra hydrogen. But in the test, this is the organic product you want to show. Remember, the key step I'm talking about is this red part, the shift. That's the new information. Okay.
So when you're trying to decide whether or not it's going to do a hydride shift or a methyl shift, I see you're labeling the carbons like beta carbon. How do you determine that it's a beta carbon? Because it doesn't have a positive charge?
No, it's the immediate carbon attached to the C+.
Okay, so then the C plus would be the alpha carbon?
Yes, because it was the alpha in the beginning because it has the leaving group. Yes.
Okay.
And you don't always do shifts. For example, in this case, you already have it as tertiary. No need of shift. In this case, you have it as secondary, right? This will be your beta carbon. This is a beta carbon. But if you push this hydrogen here, guess what you're going to form? You get a primary carbocation. Do you want to form a primary carbocation? No, because primary is less stable than secondary. So in this case, the molecule will not shift. Here, the molecule will not shift. It's already tertiary. Here, it's secondary, but shifting does not help. So it will not shift. It stays the way it was, secondary. The only time a molecule does the migration, the shift, the rearrangement is if there is a more substituted beta carbon that can help it to move from either primary to secondary or secondary to tertiary. So that's how you reason out. That's how you decide. And in deciding which carbon, which beta carbon will do the shifting, will donate a group, which could be a hydrogen methyl or methyl, you look for the beta carbon that's more substituted. Definitely, this type of carbon right here is primary carbon, right? That's a primary carbon. We did that in some earlier chapter. That's a primary. It's only bonded to one other carbon. This carbon right here is bonded to 3 carbons, so that's a tertiary. So we would rather move a group from the tertiary beta carbon, in this case, than the primary.
And then after it does that hydride shift, that beta carbon that you're moving the hydrogen from becomes the carbocation?
Yeah.
That will undergo the nucleophile attack?
Yeah, because you stole one bond from it. You see how I'm pushing my red arrow?
Mm-hmm.
You are moving the hydrogen with the bond. So it's one bond less. If you do your formal charge calculations, that carbon has a valency of 4. There's no lone pair. And then there's 3 bonds. If you subtract, you get +1. So that's why I put the positive charge on there.
Okay, thank you.
All right. Okay, so I think that's clear. Let's do more examples. Am I clear enough? Am I rushing you guys, or we're good?
That extra explanation helped out a lot.
All right, thank you. And I love the questions. Please keep asking the questions. Don't scratch your hair. You know, that's why you're here during this live lecture, so that I can iron out some of these problems. So let's look at another example. The thing is recording, so let's see. Let me confirm it's recording, because sometimes my software decides to sleep. Yeah, it's recording. So just in case you didn't finish drawing, you'll go back and play it, and I'll make sure the link is active. So let's do another example. This is all we'll be doing today. This is part of the complex organic chemistry at your level. That's why I am trying to take time to explain it fully. So again, now this time you're given this, and you're given, I'm not going to use water. This time I'm going to use methanol. It's a weak nucleophile, definitely. And then we know it's polar protic solvent. So So that's why I don't expect Sn2. Sn2 will want a strong nucleophile and polar aprotic solvent. So here I expect Sn1. Now, first step of Sn1, leaving group, bye-bye. Once you get here, ask yourself, what type of carbocation do you have? You have a secondary carbocation. The next question would be, can you make it tertiary? So to do that, determine your beta carbons, because obviously this was alpha. So the beta carbons are the immediate neighboring carbons to your C+. Okay? This carbon right here is a primary. This carbon right there is a quaternary. It's bonded to 4 other carbons, including the C+. So one would want to do a shift because it's possible to do a shift. You have a higher degree carbon, so to speak. So the shift in this case will happen by moving one of the methyl groups. You see, all of those are methyl groups. All of these guys are CH3s. So really, there's no baby hydrogen to shift. So you just have to choose one of these CH3s. And in this case, we move probably this one for purposes of chirality. Let's move that one. It moves with the bond. My laptop wants to sleep. So you're going to be left with 2 methyl groups down there and a plus sign because it's 1 bond less. And then the CH3 that moves goes where the hydrogen was. I'm going to note it down by just writing the CH3. The other one is also a CH3. I'm just writing the CH3 so that you know that's the one that moved. And then now you're going to have your solvent coming in, or the nucleophile, sorry, coming in. So let's bring our nucleophile. Okay, you use the lone pair on the oxygen because that's the nucleophilic site. We defined what that is. You can either attack from the top or bottom. Now, let me ask you, what is the hybridization of that carbon?
Tertiary.
Hybridization.
sp2.
sp2. So in other words, it's trigonal planar. That's why I'm saying this nucleophile can attack from the top or bottom. The reason I'm saying that is if you already have 3 groups here, the nucleophile will be the 4th group. You'll want to show both R and S. But in this case, I see 2 groups that are the same. I only expect 1 product because right now the carbocation is a chiral. You know, carbocations have 3 groups, right? So I can tell myself and to use that term achiral and chiral. So this one is achiral because I see 2 groups that are the same. If these had 3 groups that are different, I'll term the carbocation chiral because once the nucleophile attacks, I'll get the 4 different groups. Then I will have to show the nucleophile attacking from the top and from the bottom, and that gives you what we call racemic mixtures. In this case, that's not the case. Okay, so I only expect 1 product, and we're gonna do that example that I just described about racemic mixture. So I'm not worried about showing stereochemistry here. Usually you have to show stereochemistry if you end up with chiral carbon. So in this case, the oxygen attacked, you used its lone pair, you're left with 1 lone pair, so you're going to show a positive charge because oxygen does not like 3 bonds. It likes 2 bonds. You have an additional bond, so you have to show the plus sign. So this mechanism does not stop there. Again, you always have to finish with what we call proton transfer. So an extra molecule of the methanol, because it's a solvent, playing the role of both a solvent and a nucleophile, the extra molecule of the methanol will come in to do the proton transfer. So you'll take your lone pair right there and use it to take out the extra hydrogen. This hydrogen will go. So we do that. Okay, and that's how you end up with your final product.
So the proton transfer happens when another molecule from the protic solvent attacks the positive charge?
It does not attack the positive charge, it removes the extra hydrogen to neutralize the oxygen. Got it? So the methanol is taking out the hydrogen, and then we use the 2 electrons, the bond, donate it back to oxygen, because we use that lone pair to attack the carbocation. We need to give it back. That's what proton transfer does. So whether you're using water as a nucleophile or an alcohol, it's always going to be that second molecule. Go ahead.
I was just saying, that's because oxygen prefers to have 2 bonds?
Yes.
That it needs to go through the proton transfer?
Yes.
Is there a time when you would go through an Sn1 reaction that you don't need to do a proton transfer, or is that every time?
Always. You have to.
Always? Okay.
Yeah. You have to finish with proton transfer. So now notice that I've said this is the major product. I need someone to guess where the minor product will come from. Someone? No guess? Okay, so I'm going to define where the minor product will come from. Notice that the major product came from the tertiary carbocation. The minor product is going to come from the secondary carbocation. So if the nucleophile if the molecule delays to do the shift, and the nucleophile is like, well, it seems like you're not going to shift, I'm going to attack you anyway. So whenever the nucleophile attacks the molecule, the carbocation that did not shift, so this is the secondary one that did not shift, if the nucleophile attacks here, then eventually you're going to get the OCH3 on that carbon. But notice that this secondary carbocation has 3 different groups. You do have 3 bonds, so I'm showing the hydrogen, the third bond. You have 3 different groups. You have the hydrogen, the methyl, and the tert-butyl. So I would term this carbocation as chiral, and I'm using the apostrophes because I'm just using the term for the ease of explanation. I'm calling it chiral because it's gonna give me a product which is chiral. You already have 3 different groups. The nucleophile, once it attaches there, you'll have 4 different groups. Then you have to show both products from here. I'm assuming I'm attacking from the top. Remember, you told me the C plus is sp2. So the nucleophile, the carbocation is flat. If I were to draw it well, I should show it flat. All these groups on one plane. So the nucleophile can attack equally from the top or from the right and from the left. So assume you are doing the top attack, the topical attack. So one of these group will be flashed back, and I'm going to use the baby hydrogen to be flashed back. Okay, and then the nucleophile attacked from the top, so I use the shaded wedge. And again, now the oxygen used its lone pair, I give it a plus sign, it has 3 bonds. So you have the other option where the nucleophile could attack from the bottom. So let me use this color before I switch the pen. Attack from the bottom will give the nucleophile the dash bond, and this time your hydrogen will be flashed up because it was on the plane before, because this carbon is sp2, trigonoplanar, but now because of the bottom attack by the nucleophile, it switches the hydrogen to go to the top. as the nucleophile finds space from the bottom. So now these are the two options. Now notice that we are not done. The oxygen is positively charged. Again, I will insist one must do the last step, which is always proton transfer. So with proton transfer, a second molecule of the protic solvent, whether it's an alcohol or water, will use its lone pair to take out the extra hydrogen, because oxygen always likes to have two bonds on it. So that happens there, and then on this other molecule, the same thing happens. You take that out, this goes on there. Alright, so next you just copy out the structure. You're not changing the stereochemistry. All you did was to steal the extra hydrogen with the extra molecule of the protic solvent, in this case it's methanol. So now the methanol here is, the oxygen here is happy with two bonds on it. The methanol that attacked here now is happy. You just made an ether actually. That's an ether group. Who can tell me the relationship between these two products? By the way, this will be the minor products from this original reaction. What's the relationship?
Are they enantiomers?
Yes, enantiomers. Why? If you assign chirality, one would be R, the other one would be S. So 1, 2, 3. You're going towards your right. The smallest group is to the back. This is an R product. 1, 2, 3. You're going towards your right. The smallest group is towards you. This is an S. And because there was equal approach of the see, you're attacking from the top, or you could attack from the bottom face. Because there was equal approach of the nucleophile, that's why you get equal mixtures of these two guys. So this was from the bottom attack, and this was from the top attack, right? This product here came from the top attack. And who is attacking? The nucleophile, the methanol. So you have equal chance. That's why the final product will be 50-50 in amount. So let's say these minor products. Okay, let's first say this. Let's assume the major product from the reaction was 70%. Then each of these will be 15 and 15, which is 50% of the 30, 50-50 equal mixture, or 1-to-1 mixture. That's what the term racemic mixture means. So a racemic mixture is a mixture of products that has equal amount of the two products. Okay? So it's 50-50. I'm going to write it out here. So you have 50-50 or 1-to-1 mixture. That's what racemic mixture means. And I just use an arbitrary number here. If this is the major, then it has to be having a higher percentage than the total percentage of this. So this could be 70, 15, 15. This could be 80%, 10, 10, and so forth and so forth. So now, in summary, if you're given a starting material and you're reacting it with a protic solvent, you expect Sn1. First of all, the leaving group leaves, you get a carbocation, inspect. the carbocation is secondary. The secondary is not as stable, so it does a shift. You shift from the more substituted beta carbon, which means is the more substituted immediate neighboring carbon, which is what you have down here. Look at the groups that you have on the more substituted beta carbon. You have to move the smallest group. In this case, all of them are methyls. I'm moving the methyl, one of them. And you only do the shifting once. You don't keep shifting to make it tertiary, only once. So in this case, we did a methyl shift. I forgot to write the term there. So methyl shift, very important. So you converted your secondary to your tertiary carbocation. Okay? So your tertiary carbocation is now going to be attacked by the nucleophile. And that's why Sn1 reaction is unimolecular. Only one molecule determines the rate. The rate determining step is formation of this carbocation, which has a chance to shift to tertiary. And now the tertiary will be attacked to give the major product eventually. That's why I said major product comes from tertiary carbocation. It's going to be attacked. The nucleophile attacks and attaches onto the carbocation with all its elements. In that case, we're going to still have the hydrogen on there. Oxygen does not like 3 bonds on it, and in fact is positively charged. So we have to neutralize the positive charge by making oxygen having 2 bonds on it. So you use an extra molecule of the solvent, which happened to be the nucleophile in the first place, playing the role of a solvent and a nucleophile. In this case, we'll use it as a base to take out that hydrogen. You neutralize the oxygen. At the same time, that CH3OH now becomes CH3OH2. So that gives you the major, because the nucleophile is sitting on the more substituted carbon coming from the tertiary. The nucleophile can forget, or the nucleophile can be too quick to attack the secondary carbocation just before it rearranges. That's how you get the minor products. Okay, so in this box, I'm showing you how you get minor products. Overall, this reaction is going to give you 3 products. This will be product number 1, and these 2 will be product number 2 and 3. They are equal in amounts. So let's show how you're making the minor products. The nucleophile attacks either from the top and the bottom. And why do I need to care about the approach? The reason is because I see my carbocation already has 3 different groups: the hydrogen, the methyl, and the tert-butyl. Okay, so now we're gonna attack it from the top face to begin with. So the oxygen will have this type of wedge, which means towards or top side. Question?
I was just gonna say, is that towards?
Yeah, it's either towards or top. Remember, whenever we are talking about chairs, if you use a wedge, that means that group is on top, either axial on top or equatorial up. So you can define the shaded wedge to be towards or on top, because this carbocation can be sitting flat. I can draw it sitting flat, and that way I would easily, comfortably use the word top. All right, so either towards or on top, use the shaded wedge. So you get this product. The smallest member that was sitting on the C+ will be flashed opposite. So if this is towards you, the hydrogen should be away. If this is on top, the hydrogen should be at the bottom, whichever term you use. Now let's look at the bottom attack. So if the methanol approaches from the bottom side or from the back side, then you're going to give it the dash wedge. All right, which means the smallest member of the carbocation will be flashed towards you or on top. Now the oxygen is going to get a plus sign because now it has 3 bonds after the attack with the nucleophile. So you use an extra solvent molecule to take out the proton to quench the positive charge on the oxygen or to make the oxygen comfortable with 2 bonds. That's what you get. This functional group is an ether. That's an ether. So do the same thing here. Take out the extra proton, you get an ether. Because there was equal approach from top and bottom phase, 50-50 chance, you're going to get equal amount of these two products, which happen to be RNS of equal amount. So they're racemic mixture coming from the word race, black and white, for example. So equal mixture of RNS, different races, RNS. These two guys are minor products because they are formed from the minor carbocation. This is the major because it's formed from the major carbocation after the methyl shift. I've explained it a lot, so if you have a question, ask before I quiz you.
Are we going to have to know how to label the percentages of the products?
No. The percentages here, I'm just using them for purposes of teaching. You need to tell me if it's minor or major, but you don't need to tell me if it's 70%, 15 or what. You don't know that. I don't know that unless I do the reaction and purify the products. Okay?
Okay, thank you.
Yeah, so I'm using the percentages just as an example. It could be any number. Any more questions before quizzing you? Remember, the mechanism is standard. You just either gonna decide whether it's possible to do hydrogen shift or metal shift, and then you'll always finish with proton transfers for Sn1.
So with the top and the bottom attack, does that only happen because it's an sp2 carbon and because it's flat, that there's an option to go top or bottom?
Yes.
Because it's...
Yes, and I will only consider top and bottom because I'm expecting two products. If the carbocation does not have three different groups, no need to worry about top and bottom. No need to show the wedges. You just show regular bonds. And that's what I did here. Where? Moses, you're lying. Okay, here. You see this carbocation? I don't have three different groups. I already have two metals that are the same. There's no way I can end up with a molecule that's chiral. So no need to show wedges.
Okay.
All right. Any more questions about this before we do our regular examples? Okay, no more questions. So let's do predict the products. Okay, predict the products, predict the Sn1 products and label them as major product or minor product. In fact, let me say major products, minor products. You can have multiple. So the first one is so we're going to start simple. I don't know if this is simple anyway. The emphasis is on shifts. So that's the first one. The choices I'm giving you. It's tough to draw these things. I thought it's easy, but it's not. Let me draw again. Okay. All right, so what are the answers or answer? So I will need the major or majors, and then I'll need the minor or minors. Let's use the alphabets for purposes of simplicity of drawing. Someone volunteer?
I think E is the major.
You're saying E is the what?
Major?
E?
Yes.
Oh, E has no chance of forming.
No.
Yeah, that one is out of place. That's there to catch you, and it did. Keep trying. You know, you better fail now than when you're by yourself.
True.
Hey, I'm not gonna continue unless you guys contribute to this thing. Don't sleep on me. It's gonna help for you to draw your summarized Sn1. Assume the BR falls off. What type of carbocation do you have?
Secondary.
Okay, does it have a chance to go? Tertiary?
Yes.
Yes. What type of shift do you expect?
Methyl.
Nope. There's a hydrogen there. You expect a hydrogen, yeah, hydrogen shift.
So
You remember what we said, you move the smallest group on the beta carbon, on the most substituted beta carbon. You don't move the methyl if the baby is there. I mean, if I ask you to carry up a 1-year-old and a sumo fighter, you choose to carry the baby. That's what the molecule will do. It spends less energy to shift a hydrogen versus the methyl. Okay, now let's move on. I think these two, that should have given you the clue to give me what the major is. What's the major?
Would it be A?
All right, so notice that this carbon right here has 4 different groups. Going this way is different from going this way, and of course it's different from the methyl, so you expect racemic mixture. So now revise, tell me what your product is.
So it would be A and B?
Yes, those two will be majors. Now let's clear that up. So the water would either attack from the top side or from the bottom side, and the reason is because this carbocation is chiral, meaning you have 3 different groups. So once the water attacks, you're gonna get 4 different groups. That's the only reason why we are considering chirality here. Okay, I keep drawing 6-membered rings. I don't know why. We need 5-membered ring. Okay, so you equally could get, so the smallest group is a metal. The metal could be flashed up or down. So this is where the water attacked from below or from away. And then you're gonna get the metal flashed away if the water attacked from the top. So now this, after proton transfer, you'll get that. After proton transfer, you'll get that. So here, major products A and B. And of course, those two are enantiomers. So now someone tell me the minor product. Or before we do the minor products, what makes the minor products?
The secondary carbon.
Okay, the secondary carbocation. Now tell me what the minor product or products is. It's gonna definitely be C and D, because the water will attack this plus sign here. So if this is your minor carbocation, right? And in fact, I would say none of this. It's not C and D, because this metal should not change. That metal group should stay as a regular bond. That was an error on my part. The minor product is not listed on here. It's not C and D. I should have listed more. Let's see, where is the pen? This geometry on, come on, the geometry on the metal does not change. So that should have stayed. So the minor product should be F and G. Because this stereochemistry is not, the bond type is not affected. The water is just simply attacking the carbocation. The water is simply attacking the carbocation. It's not interfering with the metal. And again, it's chiral carbocation. One would call that cation chiral in apostrophe, in parentheses, because it's not the right term to use there anyway. So you could either attack from the bottom face or the top face. After proton transfer, you're gonna get these two guys. I hope that is clear. Do you have a question on it? Remember, the metal is not touched. That's why it's wrong to show up and down. Nothing interfered with the geometry of the metal. So it should stay the way it was, unless I defined whether it's towards or away. But the metal is not touched, so you just need to leave it the way it was. All right, so now let me, sorry about that if you're using earphones. Let me pull up the remaining ones. Let's see. I think there's a part 2.
I'm sorry, for the minor products, the methyl stayed the same, but the alcohol changed, so there would be diastereomers.
Yeah, now it's tough to know if they're diastereomers because the metal stereochemistry is not shown. But technically, if the metal stereochemistry was shown, then yes, you'll get diastereomers.
Okay, so if you're assuming that the methyl stays the same, then yes.
Then you get diastereomers.
Okay.
Okay. Come on. What's happening to Moodle? Okay. I think it's because of my recording software. It's taking the whole memory of my old laptop. I just want to finish up the chapter with a few slides. That will not take long because those are things I've already explained on the examples. Now you see how a small concept can take time in organic chemistry, and there are tons of those small concepts in the official organic chemistry class. Thank God this is just survey. Come on. Okay. Okay. Can you see my PowerPoint? Say yes.
Yes.
Thank you.
Yeah.
All right. So now this is just the rest of the part 2 of chapter 8. So now I think I've done something similar with this molecule. So if you lose that, then you're gonna get a carbocation right here, which is secondary, and then the secondary carbocation will want to migrate to make a tertiary. So the CH, let's say we are migrating this guy, so that CH3 will be here. That's a metal shift. Okay, you're left with 2 metals and the plus sign is now there. That's a tertiary. Only then will the nucleophile, your methanol, come into attack. Now, this is not, you don't have 3 different groups, so I don't need to care about showing chirality. For this one, I'll just attack and move this one here. So generally speaking, my product after proton transfer will give me an ether. But I'm going to draw the proton transfer step because I'm just summarizing what we discussed. Okay, so you get OCH3 after proton transfer. One would say, I don't see the answer. None of this is the answer. The reason is because the book went one more step further than the survey organic to explain something else. So whenever this metal is going to attach to the plus sign, this C plus is planar, trigonoplanar. The metal can attach from the top side to get that, or the metal can shift and attach from the bottom side to get that. But eventually, each of those carbocations, whether this is on top or the bottom, will be attacked with the methanol here. So really the answer is 1 and 2. The key point for you guys is to know where the metal eventually ended. This is the product. That's the methanol right there. And this is the methanol attached to the carbon with the 2 CH3s. So the answer here is 1 and 2, which is A. The only difference in this case is how we are getting the chirality. This metal shifts either attaching from the top face or the bottom face, but that's one more step in the official organic class. That's why you're seeing it here. But for me, I don't want you to worry about putting your metal on top face or bottom face. Just take it as a normal bond to avoid confusion. So 3 and 4 are minus. We are looking for the major. 3 and 4 are minus, just in case the methanol decided to attack the secondary carbocation yes, you're going to get 3 or 4. 3 and 4. But we are looking for the major. The major will be 1 and 2. Having the methanol, the OCH3 attached onto the more substituted carbon. Okay. This is a summary of what we already talked about. So Sn1 would prefer tertiary. Sn2 will not want tertiary because it's going to be crowded. For example, if you have this group, that's a tertiary, the backside is crowded, the nucleophile will be shunned away. So Sn2 doesn't like tertiary, Sn1 prefers tertiary because once the leaving group leaves, you get a tertiary carbocation which is stabilized by electron donation through bond. Sn1 does not like Sn1 does not like metal substrate because these tend to give you metal carbocation which is unstable. But Sn2 will very much like the metal halide. Why? The backside is open for the nucleophile to attack. So the preference of the electrophile structure is opposite for Sn1 and Sn2. Sn1 will prefer the most substituted electrophile. Sn2 will prefer the least substituted electrophile because there is little sterics on the backside. On tertiary, there's a lot of sterics or crowding on the backside. The nucleophile will not enter to attack. For Sn1, the nucleophile only comes later on. So the rate determining step is formation of the carbocation. So the more stable the carbocation is, the quicker the Sn1 will love to go. So this is just a summary of what we talked about last class. Will this molecule go Sn1 or Sn2? Someone tell me.
Sn1?
No, it's going to be Sn2. This is a secondary substrate. Acetone is a protic. And of course, this is a strong nucleophile. You see it has a
the negative charge.
Negative charge, yeah. So all pointers, of course, the secondary substrate can go either Sn1 or Sn2. So we don't look at the structure of the electrophile. We look at what's provided on the arrow. So definitely Sn2 for the reasons written on board. What about this? Consider this as a living group. Don't worry about how ugly it looks. That's the living group. So these are secondary alkyl electrophile. It's a secondary electrophile. This is protic solvent plus it's neutral, so it's a weak nucleophile. So definitely we have to go Sn1. Okay. Remember, secondary substrates can either go Sn1 or they can go Sn2 because they are right in the middle of the ranking. So we have to look at what's provided on the arrow for secondary substrates.